baseball problem. A runner is moving toward first base at a rate of 24 feet per second. How fast is the distance between second base and the batter changing at the instant that the batter is midway between home and first base? Let S be the distance from second base. Right? So notice that that's going to be changing. Right? So it's right here. And it was the most, right, when he was back here. Right? That would have been the farthest distance. But as he's moving this direction, that distance is decreasing. And again, when he gets all the way to first base, right, that'll be the smallest distance. Right? So let S be the distance from second base. Let F be the distance from first base. Right? So as he's running closer to as he's running from home plate to first, of course, that distance is decreasing as well. So the distance between the runner and second base is decreasing. The distance between the runner and first base is decreasing. The only thing that's not decreasing is the distance between first and second base. Right? That's going to stay 90 feet. Nobody's moving the bases around. All right, so we're given one of the rates, and we're looking for the other. All right, so we're given that the runner is moving toward first base at a rate of 24 feet per second. All right, so we have df dt. That would be negative 24 because the distance is decreasing. They're not going to tell you whether the rate of change is positive or negative. You have to think about the situation. All right, here, if someone's running closer, the distance is going to be decreasing, so the change will be negative. So we want to find ds df when f equals 45 feet, when the runner is halfway between home and first base, and the distances between any of the bases is 90 feet. All right? Where we know df dt is negative 24 feet per second. We can relate that because using Pythagorean theorem to relate the distances, because this is a right triangle right here. Right? So f squared plus 90 squared equals s squared. Right? So we're going to take the derivative, but I want to point something out. Right? Notice I have a number in there, and there's only one time you're allowed to substitute a value before taking the derivative. You may substitute a value before taking the derivative only if it's a constant, or use a variable and then make the rate of change 0. Because one thing we know is that the rate of change between first and second base is not changing. That's always going to be 90 feet. Right? What's changing is the distance between the runner in first and the runner in second. So let's take the derivative. Right? So the derivative of f squared would be 2f. Derivative of any constant is 0. And, oops, almost forgot something. We're taking this with respect to time. Don't forget the dt. So it's 2f df dt, right? Because this is implicit differentiation. It's the derivative of f with respect to time. The derivative of the 90 squared is just 0. And the derivative of s squared would be 2s ds dt. We're looking for ds dt, so let's isolate ds dt. So we have 2f df dt. And I do this before I plug anything in. And then may as well get rid of the 0 and at the same time. So equals, so if we divide both sides by 2s, we will have ds dt isolated. Now that we have it isolated, let's substitute for the values. All right, so we have ds dt is equal to, right, so we have 2, and then f is 45, right, because we're taking the derivative when he's 45 feet away. Df dt is negative 24 feet per second. You can leave out the units until we get to the end. And then we're going to divide all of that by 2s. And we have one little problem. We don't know what s is. But that's a small little problem. We have to solve for what s is. So I didn't bother to think about whether I had all the values, but if we just stop right here, we can go find s. And we can find it because we have a right triangle. We can use Pythagorean theorem. Right? So s squared is equal to 45 squared plus 90 squared. So that's going to be, grab a calculator, 45 squared the calculator is being difficult. Well, it worked earlier today. I think this one works. Yep. Whoop. I had a number in there already. Let me do that again. So 45 squared, yeah, 2025. This is 8100. All right, so S is going to be the square root of 10125. It is fine in these kinds of problems to get a decimal equivalent. Just don't round too much. Include four decimal places. That should be fine. And take the square root. So that would be 100.6231. All right, so now we'll just substitute that value for S. And I don't have a whole lot of space, so I'm just going to simplify. Well, actually, no, we can cancel out the 2's. So this is just going to be 45. Oops, I hit an extra 1. 45 times 24. And then divided by, oops, the answer I got from the last part. So that's 107. I guess that sounds right. I'm trusting I hit the value incorrectly. 107 point, yeah, that sounds all right. 107.1, gosh, it's a hard calculator to read. 16651. Oh, and it's negative. I didn't put the negative into the calculator. So this is, because the distance is decreasing, negative 101 point, or excuse me, 107.6651. I have all these little lines on this calculator. My good calculator is at work. It'd be nice if I brought it home. At home. It'd be nice if I brought it to work. All right, and so that is all there is to it. So you're going to find that a lot of times your related rates problems can be rewritten in terms of a geometric formula. All right, so I'm going to end this podcast, and I'll see you for another problem in the next one. Bye for now.